Edexcel called Pure Polar Coordinates, Polar Curves, Finding Areas. You should be familiar with the formula for the area of the sector of a circle, which we can see here. The area of a sector is a half r squared theta, and we can think of this as being the area, it's theta radians out of a possible 2 pi radians. It is that fraction of the entire circle, which would be pi r squared in area. So that's where theta equals a half r squared theta. Theta is measured in radians, really important. That's where this formula came from. We can now look at the area enclosed by a polar curve, and the area enclosed by a polar curve can be thought of as the area of a sector with a variable radius. There's a more formal proof of this in your text, but basically what you're doing is you're considering a very thin slice of this area where the angle in there is delta theta. So you're looking at a series of very thin slices, and when you find the sum of those areas, you can show that the limit will be the integral of a half r squared d theta. It's worth noting as well that this area is swept out from theta equals alpha to theta equals beta, which would be the limits of this integral. So that integral will find the area swept out by a polar curve between angle alpha and angle beta. So here we're going to find the area enclosed by the polar curve r equals sine theta between pi by 6 and pi by 3. It may be useful to just do a quick sketch, particularly if you're not too familiar with some of these polar curves. So when theta's naught, r is naught. When theta is pi by 2, the distance r is 1, and when theta's pi, r is naught again, and we are in fact looking at a circle. We want to find the area swept out by the polar curve from theta's pi by 6 to theta's pi by 3, so the area is going to look something like that. There's just a rough idea of the area going from theta's pi by 6 up to theta's pi by 3. So the area is half the integral of r squared, which is sine squared theta. Common mistake is students forget to square the r. R squared is sine squared, and we're going from theta is pi by 6 to pi by 3. So integrating sine squared, we've seen before that the integrating a trig ratio squared can be tricky unless we exploit the fact that we know that cos 2 theta is 1 minus 2 sine squared theta. Therefore we can rearrange for sine squared theta. So this area will become a quarter of the integral from pi by 6 to pi by 3 of, and when we rearrange this, we're going to get half of 1 minus cos 2 theta. I've already put the half out there with the other half to make a quarter, so we're going to be left with 1 minus cos 2 theta d theta. Now, because we haven't got a trig ratio which is squared, we can integrate this to get a quarter of theta minus sine 2 theta, and notice because we're integrating we need to balance this up with a half from pi by 6 to pi by 3. So I'm putting the limits in now. So here goes the top limit. So pi by 3 minus a half of sine 2 pi by 3 minus a quarter, and now we're putting the bottom limit in. Pi by 6 minus a half of sine 2 pi by 6, which of course is pi by 3. So here we're going to get a quarter, pi by 3 minus, and this will become sine 2 pi by 3 is root 3 over 2, so this is root 3 over 4, and this one is a quarter pi by 6 minus, and sine pi by 3 is root 3 over 2, and times by the half is root 3 over 4. And when we expand the brackets, the minus root 3 over 4 term and the minus root 3 over 4 term will cancel out, and we are left with a quarter of pi by 3 minus pi by 6, which is pi by 24. So that is the area, the exact area swept out by this polar curve between pi by 6 and pi by 3. So the key things to look out for, the sketch is helpful, but the key things to look out for, make sure you've got the limits the correct way around and you know with the angles which are sweeping out this area. Make sure you've got the r squared term. It's very easy to deal with r and forget the r squared. And because it's sine squared, we needed that double angle identity to make sure that we had something that we could integrate. And the beauty of this method is it will give you an exact area. It isn't an approximation. So in the next video, we're going to be looking at parallel and perpendicular tangents to the initial line.